We were talking about lab versus field. So let's just take a look at a wall design. This is a particular wall design that we used on a project. This blue curve is the STC curve for 63. This red curve is the test in a lab that met STC 63. Now you notice, and I probably should scroll this down so you can see the frequencies. Up here around 2.5 kilohertz, there's this big lack of performance, and then it starts performing much, much better past that. Down in the lower frequencies, below 250, it stops performing as well, and then even though this is not technically part of the standard, they show it anyway. So this is a lab test, and it shows you that this curve they've developed, nothing is typically going to actually look like that. Now let's look at a field test of that wall built on a particular job site we did. Here's the actual field test, and you'll notice there's not a dip at the same frequency in this particular application. There's a dip here at 400. There's an improved performance at low frequencies and some other factors. Now, this is technically the same wall, but when the contractor put in to build the wall, they substituted a couple of products, and it isn't really built exactly the same way. The other thing that happens is how much glue is used, how much caulk is used, how many screws are used. So this lab test versus this field test, you have some significant differences. Now, if I had known it was going to perform like this, I might have used a slightly different wall. When I was looking at this originally, this was a particular music rehearsal space. This lack of performance up here is a problem for brass instruments and some other things that might bleed through this wall. And this lack of performance at low frequencies is potentially a problem for percussion, bass guitar, other things. So if I was looking at this, and this was a cost-effective wall design, I mean, normally when we're designing for music, we design much higher than 63. This just gives you an idea of the fact that not everything is equal. Things perform differently in the field, and things perform differently across the bands of the STC curve. So you don't have all of the same things happening all the time. Now let's get off to one of my rants. This is another rant. I was talking about mass-loaded vinyl. Let's look at some MLV realities against a piece of 5/8" gypsum, which you can see there. And then there's cheap MLV, which is thin, and premium MLV, which is thick and also uses a better filler. Now the interesting thing you'll notice is that dip about 2500 that we saw in this lab test is also in the sample of, this is just a sample of a single sheet of gypsum. This is being generated by a computer program that we're using. And when you look at MLV, MLV does not have that dip, but it has a dip at lower frequencies. And then the cheap MLV is significantly lower performance than the expensive MLV. Now the question of whether or not one is really identical to the other, hard to say. But basically you've got different types of mass-loaded vinyl. Now the theory is that you take MLV and you stick it in a wall, it fixes all of this. And it might, but that depends on how it's installed, because one of the things nobody ever wants to talk about is when things are in contact with each other. So mass-loaded vinyl, this number here, and this is a common MLV, there is no magic, there's no MLV out there that is so much better than all the other ones that it doesn't look very much like this. There's slight differences between them based on their densities, but you get into the same class of product, they all look pretty much the same. But this is a free hanging sample. This is tested in the lab, free hanging in an open space with an airtight envelope. Same thing with JIP. So you've got these conditions that aren't the real world. These aren't the way you build things. So if you take MLV and you sandwich it in between a couple of things, or even you put a layer of drywall over it, it's contacting the MLV, you're not going to get this free field performance. The other thing is if the MLV is across stud framing connected too many times or is touching things too many times, you're going to have some variances in this behavior. Not to say it's a bad choice, it depends on what you're doing. But what's interesting is one layer of JIP across a lot of the frequencies of concern in construction is pretty much the same as one layer of premium MLV for a lot less money. So now let's take a look at something else. We're done ranting, I guess, for a moment. Let's take a look at 4 constructions, and these are theoretical constructions. And to be honest, this software doesn't take everything in the world into account, but it takes a lot of stuff. So one of these is gypsum, 1 layer, which is in blue, and that just shows you what happens. Then this is gypsum, 2 layers, directly applied over the one, and you get an increase that you would expect based on having 2 layers, but you also have some variances that occur up here in this frequency dip. Now, the interesting thing then is let's put an air gap, and in this case we put a 3-inch air gap between 2 layers of gypsum. Look what happened. Having that air gap created a resonance and spring condition in between the materials. It created a whole bunch of weird anomalies and lowered the overall performance of the system dramatically. So then we add bad insulation into that air gap, and look what happens. So the bad insulation takes all of the resonances out between these surfaces. So I guess what I'm trying to get across here is that people do all sorts of odd things. We've seen people take an existing wall, put a piece of MLV on top of it, and another piece of drywall. And we've seen people take an existing wall and put a stud on it and add another piece of drywall. All of these things have completely unreasonable behaviors. What they are is going to depend on what you did. Now, when you start adding mass, you get a simple additive mass that is predictable. When you start adding multiple materials and you get into doing all of those kinds of things, you end up with spring-loaded behaviors and other things that are really hard to know. Now, even this software, this doesn't take into account all the stud framing and everything else that's actually in the wall, but it takes a look at the resonant frequencies of the materials, their characteristics, their modulus, basically how they bend when sound hits them. And it gives you an idea of some of the things that can go wrong. So when you're starting to look at designing for soundproofing, there's a lot to look at, and there really are no magic new solutions out there, no matter what anybody says, that solve everything no matter what. So anyway, that's kind of an overview of that part of it. Next thing I want to talk about is if you want a wall, so this is Wall Construction 101. If you want a wall to actually behave the way the lab test would make you think it behaves, you need to do a few things that aren't typical in the way you present it to a contractor. This is a typical section that we see from an architectural set of drawings of a wall. Not a whole lot of information there. There's some things shown that are there, but they're not described. Now, contractors are notorious for not even taking the drawings in the field, but they take the specs even less often. So if you want something to actually behave properly, anywhere close to the design STC, this is the way you draw a wall. So you note that there's supposed to be 3 layers of acoustic caulk across the top of this stud, 3 layers of acoustic caulk across the bottom of this stud, that you have to use electrical back boxes with foam gaskets and also with fire stop putty pads, which is basically a wraparound soundproofing package that goes on the back of the outlet to seal it. So everywhere you got a gap in there, and there's ways you deal with other penetrations. There's a lot of different details that you get into, but you have to do these basics just to get close to a lab test. Then you alternate your layers of gypsum, alternating layers. You don't have them touch the floor. You put a spacer in, you have them lifted 1/4 of an inch off the floor, and then you caulk that gap on the bottom and on the top. Now, in an ideal world, you would also do that at the perimeter of the wall, but in the real world, it never happens. unless you're doing a floating wall on rubber isolators or some other type of isolator. Another thing, we're showing what's called Ultra Stud here. Dietrich Ultra Stud not only builds better, but it has better acoustic characteristics than standard studs because it's full of little dimples on the face, which decouple the gypsum from the stud itself. Now, all these things are, points, small numbers of points. We also like to have them use caulk in between layers. We like to have an X pattern of caulk across the sheet and then a layer of caulk in 1 inch off the sheet on all sides. It just tends to dampen a little bit. Now, the weird part is if it's screwed in properly, that'll all flatten out a lot. But it does, in our experience, has helped a bit with some of the variances in walls. The other thing you got to look at is what kind of insulation am I going to use? And there's a lot of stuff out there online about this. Bad insulation, standard fiberglass, is what most people get. And with that, you need to get an acoustic batt insulation. There's a lot of people who make them. They stay filled in the cavity better and they tend to not settle as much. But fiberglass insulation does settle. So over time, you're going to have a gap at the top. You might have gaps elsewhere. So the question is Rockwool worth it? Which is a significantly more expensive type of insulation. In our opinion, if you're really trying to soundproof, it absolutely is. It stays in place better. It's denser because it's built out of rock instead of glass. The other thing with it is it does not settle over time, so it holds its dimension. But there's a huge difference between mineral wool and rock wool. So you've got to be sure you're actually getting rock wool, and that the mineral wools that are out there, there's all sorts of configurations. They're considerably different. Some of them have settling problems. Some of them don't have quite the same acoustic value. But when you get into looking at the actual acoustic value of the product by itself, tested by itself, Rockwool has significant advantages at low frequencies and significant advantages overall. Whether it justifies the cost depends on your application. And that's where I can't stress enough, you have to look at application. Am I designing for an office? Am I designing for a classroom? Am I designing for a recording studio or a broadcast facility? We design walls in some cases that you can't test the STC through because they're that high. They're 85 plus. You can't actually generate enough sound safely to actually test through those structures. So our rule of thumb is if you can't hear bass through it at 115 dB, you're probably STC 85 or thereabouts. Because when you look at the way things behave, if at low frequencies you're getting enough deadening through it, you've kind of got it all there. So this gives you at least a little bit of an idea that if you want to even get close to the STC you've asked for, you have to look at all of these details and make sure they're followed. Now, one of the things that's really frustrating, ranting again, one of the things that's really frustrating, the field performance of contractors. Contractors have a funny way of trying to hide things that they don't think you're ever going to see. So we've got a wall that was built recently at a project where it was testing in the 46 range. It was STC 63 design, should have been testing around 58. And we've had these built on other jobs where they work just fine. So we get down to the job site and we find gaps around the ductwork. We find gaps in places that you can barely find, up in ceilings, places where there's a conduit punched through a wall and there's a half-inch gap all the way around it, all these things. So we started wondering, what have they done? In this particular wall, there was also a vibration isolation system using resilient channel and rubber isolation mounts to get low frequency performance that was included in the job. And that particular system ended up, let's say, not being installed properly. But the only way to find out was to cut a hole in the wall and stick an inspection camera inside. So as we're going through the wall with the inspection camera, we're supposed to have 2 layers of drywall and these resilient channels with these rubber isolators sitting in there. And we go in with the inspection camera and we notice in some places there's only 1 sheet of drywall. Like they ran out of drywall, so there's like 2 or 3 feet of space where there's a layer over another layer with a big, huge gap. So I'm guessing the guys in the field, it was like a Friday and they decided it didn't matter. Well, it's funny how those rooms test differently than ones where there's actually 2 layers of drywall. And then if you look at corner details with the inspection camera, and some of these images are included so you kind of look at some of these things, you look at the corners and there's places where there's big gaps at the corner. It's supposed to meet in the corner. It's like meet in the corner. The other thing is there was supposed to be a caulked perimeter with these isolators, and the isolators are never supposed to touch other metal. You basically have a spring attached to a channel that's floating the drywall, and it's never supposed to touch other stuff. Well, it's funny, inside the wall with the inspection camera, you find that that's exactly what's going on. So I can't caution you enough. If you're doing anything, if you're building something you care about, or you're not doing it yourself, you have to have field inspections by qualified people. This was being inspected by the construction manager, who theoretically is supposed to follow the drawings and make sure they know what they're doing. When we got down to the end result, the contractor was like, well, I didn't understand any of that. And it was in the submittals they had provided. So they had submittal drawings they did that matched the design drawings that said to do all these things. And yet they somehow didn't understand it. And now they're fighting about whether or not they're going to have to fix it. And like I say, I can't stress it enough. This is a job where, I hate to use terms like they were too cheap, but let's just say occasionally people don't want to pay for us to be out in the field. So it wasn't the architect, it was the client that doesn't provide money for site supervision, in my opinion, by qualified people. And construction managers, there are some who are really good, and there's a lot of them who are mediocre at best. And they don't even bother to learn the drawings in many cases. And I hate to sound that way. And the contractors, you need an acoustic contractor, not just a drywall contractor. So anyway, these are rants that they go on about. It's not like every job goes south. If they did, we'd probably be out of business. But when they do go south, we end up out in the field defending our design by having to open up walls and argue about things and find, obvious problems in the field later. So anyway, just a word to the wise, if you're going to spend money, if you're going to build it, either build it yourself or hire somebody who actually knows how to do it and make sure someone's field inspecting it while it's going together. So that was the end of that file. So I'm thinking somehow we turn this into 2 videos. I'm going to be doing more videos on soundproofing and privacy. I'm just not ready to do them yet. So we'll get into that. And I'm going to go take a look at some stuff here and decide if it's time to do the Room of 1,000 Echoes or not. So anyway, I'm going to stop these cameras. And then I'll probably offload these videos and we'll blah, 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 blah.